All right. Again, you should be working on your reading notes if you got some of the numbers correct already. Okay, number one, which statements about mixtures are correct? They can be elements or compounds, true or false? Mixtures, true. Salt, compound, that's compound in water. That can be a mixture, right? All compounds must be in the same phase. Meaning, if it's liquid solute, it has to be liquid solvent. That true or false? False. Why? I'm thinking of noodles right now. That's liquid, right? Can I put like vegetable? Can I put the actual ramen, which is solid? Does it need to be in the same phase? No. So it can be in different phase. In fact, we have a word for that mixture. Heterogeneous mixture. So this is wrong, this is correct. The components retain their individual properties. Yes, right? They don't chemically bond, so they retain their properties. Questions with one? Number two. Which factors affect the volume of an ideal gas? So either temperature or pressure, right? Standard temperature and pressure. And this is like, what the heck? Does it have anything to do with the empirical formula? Regardless of the empirical formula of your gas, any 1 mole of any gas, so any empirical formula there, will always contain 22.4 dm³ volume. So empirical formula has nothing to do with the volume of your gas. Miss, can you be more precise? For example, if I have methane gas, that's H4. If I have ethane gas, C2H8. See, this is a molecular formula, right? But regardless whether it's in the molecular formula or empirical formula, both of these gas will have the same volume. 1 mole of both of this gas will have the same volume. So cannot affect your volume of your gas. Sublimation, straight up from your memory, the triangle. Solid to gas, right? So which is solid to gas here? B. By the way, gas to solid, what is this? Deposition. Gas to solid, deposition. Solid aqueous, aqueous liquid. What is that? Well, just this solid becoming liquid. Oh, there's gas there. So these are all of the different phases. I don't have a solid going to gas here. Ah, this is a phase change, right? This one is a chemical reaction now. We're looking at many chemicals. For phase change, you're just looking at one substance as it changes different phases. Okay, next. Ooh, interested to know why. Who got 4 right? I thought that was easy. Number 4. Nobody? Yeah, I remember. I'm like, I had to stop and look at everyone's. It's happening in 4 here. Okay, let's try to understand the question. Why do gases, remember I was talking about ideal gas, once you change the pressure or the temperature, they behave as a real gas. Their volume changes, right? Okay. Who answered B? C? C, okay. B, Bailey. Who answered D? Okay, there's many from D, so let's start with D. Collisions between molecules occur more frequently as pressure increases. That's true or false? Just the concept. True. Okay. If you increase the pressure, there's more collision. They collide more. If they collide more, do they behave as a real gas? Okay, very good. Because what I can say here is this is correct, but it's not addressing the question. The question is asking, why do they behave as real gases? Why do they deviate from the ideal gas law at high pressure? Why do they become real gases now? Hold on. Let's go to C. Increasing the pressure increases the temperature of the gas. Okay, that's also correct. What changes if I change the temperature and the pressure? The volume, right? So how do I know if it's a real gas? The volume is now changing, correct? So letter B, cohesive forces increases the volume from the ideal. If I increase the pressure, this is almost correct. B is almost correct. But then if I increase the pressure, what happens to the volume? If I increase the pressure, volume decreases. This could have been correct. Cohesive forces, this should be decreases the volume from the ideal. Could have been, right? So this is C and D correct, but it's not answering the question. A is the correct answer. Molecules have a finite volume. That's why they become real. If this is infinite volume, think with me. If this is infinite volume, even when I increase the pressure, the volume is going to stay the same. There's still going to be an ideal gas. Think with me or pretend you understand. If I say this is infinite volume, then gases will always behave like an ideal gas. They will never behave like a real gas. Because even if I keep increasing the pressure, if I keep changing the temperature, volume will not change. They're still an ideal gas. What is an ideal gas to begin with? Avogadro said, at standard temperature and pressure, they occupy. Okay, new curriculum. Is it 22.7, 22.2.7? He said, ideal gases occupy that volume at standard temperature and pressure. Meaning, if I change the temperature and pressure, the volume will change. It will behave as a real gas. So why do gases deviate from being ideal? Because their volume can change. That's basically what A means. Molecules can change, or like gases can change their volumes. Okay, be careful next time you answer thinking questions like this. All right, number 5 is a repeat question, right? So should I explain this more? Just tell me honestly. If not, I'll move next number. Pass? Pass, everyone. 6. Pass? Pass, right? Solute. 7. Pass? Okay, stop. Number 7. Okay, for number 7, you have volume, you have temperature, you have pressure. The question is, in under which conditions can your methane have the same number of molecules? So if we're talking about number of molecules, we are talking about the mole, right? Right? Because a mole is 6.02 molecules of anything. So for this one, you have temperature, volume, and pressure. Obviously, you're in your brain, maybe I need this, PV and RT. And that is asking which one can have the same number of molecules, then maybe I need to isolate mole, which is PV over RT. And then you calculate for each one. Check which will have the same number of molecules as this. So let's start with this. What is the number of molecules there? Pressure is 1. Volume is, for the sake of world peace and time, I'm not going to convert because this is cm cube anyway. Yes, it's okay. Yeah? 100 or 8.31. This one I will convert because that plus 273 can change your temperature. So 27 plus 273, 300, right? Calculator, what's the number here? This is my best in calculator class, yes. 4,000. 11. 4,000. 11. Okay, before I calculate everything, who answered A? Who answered B? Who answered C? Bailey, what did you answer? B? A, B, C. Okay, so I have to discuss everything. Let's start with A. Why is it not A? So, if you answer A, then pressure is 1, volume is 50, 8.34, 8.31. 54 plus 273, please. Okay, calculate that, please. What's the mole? One eight one four, and you're like, no, 1840. So CJ, do you understand why it's not correct? It's not correct. It's not the same mole. I'll get back to you. Letter B. If you answer B, what do we have in B? 1 times 10 to the negative 5 times 50 divided by 8.31. 327 plus 273. 600. Calculator, if B, what's our mole here? 1002? 1002. So again, no, they don't have the same moles of your gas. You go to C. You know what? I'm going to skip C if you understand how I'm calculating this. But look at D. Solve with me. So for D, you have 2 times 100 divided by 8.31. 327 plus 723, is that 600 you said earlier? Okay, calculator, I'll pretend you calculated. It's the same. Therefore, in this conditions, I have the same number of moles as my given in the problem. CJ, what was your question for A? Shorter method. Oh. Okay. But if you guess this though, so the pressure is the same, you have the volume, and then you double the temperature. Is there no, what did you answer? Okay, show me like. All right, number 8, which represents empirical formula, just looking at it, is C. What is the empirical formula of this? A? CH2. B? C? D? Again, if you get this right, you don't need to listen. You can work on your reading notes, please. If you don't want, okay, that's still fine. All right. Some people got this wrong. Number 9. Which statements are correct about Avogadro's constant? Well, Avogadro said 1 mole is 6.02, right? Of anything. It's a unit we can use for anything. So for the first one, is this Avogadro's constant? Well, you know that sodium plus hydrogen, total 24 grams. That's 1 mole. Why am I the only one writing? Did everybody get this right? 1 mole is 6.02. In this case, this is a molecule. And in 1 molecule, You have how many ions? 2 ions. Okay, just by looking at it, 12 times 2, 24, divided by 24, the same as 6.02, right? So 1 is correct. This is. Okay, number 2. It is the number of molecules in 22.4 volume of your hydrogen gas. So this is an ideal gas. 22.4 dm cube in 1 mole. Right? 24 dm cube. Okay, let's do some actual calculation. So you have 22.4 dm cube of hydrogen gas. You know that 1 mole of any gas is 22.4 dm cube. And you know that 1 mole is 6.02. So, is this Avogadro's constant? Yes, cancel, cancel. It's still 6.02. Yes. It says at there, standard. Check the conversions, but this is STP already. What did you mean? Did you calculate this differently? Ah, okay. So put a note there to yourself. This is also STP. You can ask me, during the test if you're unclear too. All right. It is the number of atoms in 12 grams of carbon. So you calculate again. 12 grams of carbon. You know that carbon is 12 grams per 1 mole, right? And you know that 1 mole of carbon is 6.02 times 10 to the 23rd atoms. So, cancel, cancel, 6.02. So 1 is correct, 2 is correct, 3 is correct. Okay, number 10. Which is the best description of atomic mass? Relative atomic mass. It's in your textbook. Okay, first of all, you choose between C and D. Maybe you're like, oh, that's the longest choice. Maybe it's correct. In this case, yes, either C or D. Okay, what's the difference between the two? The first one says it's the weighted mass of all the isotopes of an element compared to the mass of carbon-12. Sounds correct. But look at D. The same, but it's compared to 1/12 of carbon-12. Did I emphasize 1/12? I remember I was drawing. Why 1/12 of carbon-12? Because 1/12 of carbon-12 is 1. Right? So that's why we can conveniently use carbon-12 as our standard. Because it so happened that carbon-12 has 12 grams. 1 mole carbon-12 is 12 grams. So our standard is 1/12 of carbon-12. Because 1/12 of 12 is 1. Yes? Okay. All right, number 11. I think this is in the book, but let's see. You have volume and pressure. Let's put PV and RT again. You look at the equation. If pressure increases, volume decreases. So, which is the closest to here that might be correct? A and D, right? Okay, I'll choose between A and D. By the way, B is just plain wrong because look at that. The y-axis starts with some volume already at 0 pressure. What? Is that possible? No. And C is also wrong because if you increase the pressure, do you also increase the volume? That's what it means here. So no. So we're left with A or D. If you want to be very simple, okay, A is correct. But if you want it to be complex, A is actually not completely correct. Although you're telling me volume is decreasing as you increase the pressure, the relationship is not uh, linear. The graph should look something like this. There's a big decrease in volume initially. There's an exponential decrease. Now, what's happening? Brain break. Oh. Okay, so the only problem with A is that there's no linear decrease. The decrease is not linear. It should be exponential, and it tapers off. However, if you get the inverse of pressure, it will show you as you increase the inverse of your pressure, the volume increases. Yeah, I mean, have you seen this in algebra, x and y's? Um, so graphically, this is more accurate than this one. Okay. This is helpful when you want to calculate the rate, by the way, in the future in kinetics, because normally chemical reaction goes really fast and then it slows down. Ooh, that sounds familiar in biology. At first, it increases really fast and then it slows down because enzymes are now saturated, right? Now, if you want to describe to me the rate, it's hard to explain the rate by giving one value because it's fast here, slows down, and then the rate is constant here. Well, what I can do is get the inverse of my x to give me a linear increase. Then that's better representation of my rate. But anyway, this is in your book. Correct me if I'm wrong. The graphs of Boyle, Gay-Lussac's law are all there. Okay, next. So the concept here. Solutions. What are solutions? Solute dissolved in a solvent, true or false? Yes. Solution is a mixture with two or more substances. Sure. Concentrations can be expressed in grams per dm cube. True, but in IB, what do you need to know? Concentration in moles per volume. That's why I inserted that at puzzle because of this question. It can be mass per volume also. Next. Okay, so, this is a repeat. Should I skip? Okay. If you get this still wrong, there. Or maybe I can draw something like this that my student draw on the test. Oh, I can't draw it. She drew like the nun on the test. Actually, in her paper. There's like, because maybe the question is scary. I don't know. Okay, number 14. Oh, this is when I said I didn't teach that in class, so put a smiley. And then she put like face, 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 and then the nun. All right, number 14. Um, you have ammonia, very strong smelling, dissolved in water, and you have that amount of your solution. Which statements are correct? Ammonia is the solute. Water is the solution. True or false? Make that true. Water is the solvent. What is the solution then? Ammonia solution. That's the solution. Okay, the concentration is 17 grams per dm cube. You need to calculate, right? So mass per volume, our mass is 8.5. Our volume is 0.5. Our answer is 17. Yes? Okay. 17 grams per dm cube. So that's correct. The concentration is this. So concentration is mole per volume. What's the mole here? 8.5 grams. How many grams? NH3 molar mass. Sure? 26? 0.5? Yes. 17. Okay. 17 grams. No. N plus 8 plus 1 plus 1 plus 1 is 17. Okay. And your volume is 0.5. What's the answer? Is this 1? This is DMQ. All right, one last. And then we go to your calculations, and then you can work on your reading notes. Many of you got the calculations right. I was surprised, like, you had more mistakes in the concept, in the knowledge. All right, number 15. Guys, this is straight up the definition of Avogadro's. He said, at a constant pressure and temperature, 1 mole of a gas has this volume. So you have this volume per mole of your gas in constant pressure and temperature, right? Correct. Correct, correct.
Oh my. I thought of the 6.02.
Oh. Okay. Remember, Avogadro is for gas loss and also for your 6.02 number of molecules. All right. Moving forward. I want to see people doing their reading notes instead of staring at the screen because you got this right already. Just stop and ask for questions you got wrong. So how many atoms of nitrogen in this given? So 0.5 mole of NH4 2CO3. 1 mole of NH4 2CO3 is how many atoms of nitrogen? How many? 6.02 times 10 to the 23 molecules first. I'll just put mole of your, too lazy, NH4 2CO3. And in 1 mole of your NH4 2CO3, you have how many nitrogen atoms? 2 atoms of your nitrogen. And so the units, 6.02 times 0.5 is, okay, don't need calculator, right? Times 2 divided by 2. It's the same as 6.02. Questions? You got that wrong? How? This molecules, 1 here, by this. Oh, so you just counted straight. So 2 divided by 1. Well, that's a common mistake. Common mistake. Always think if mole is involved, 6.02 is involved. Okay. Okay. 17. How many grams of your product are needed to produce this volume of your gas? Solid, gas, solid. Okay. So you have 68.1 dm cubed of your N2. Avogadro said 22.7 volume in 1 mole of any gas. In this case, N2. If you look at the equation, you have 3 moles of your N2 reacting with 2 moles, right? So the ratio is 3 mole of your N2 reacting with 2 mole of your Na and 3 sodium nitrite. And you know that 1 mole of Na3 is how many grams? It's already given, 65 grams. So cancel all the units. The answer is, you're left with grams as your unit. 130 grams. So C. Number 18. What is our balance equation here? Anyone? Because I don't want to waste time. 1, 2, 2. Correct answer is 5. Okay. Number 19. Which compound has the greatest percentage by mass of nitrogen? Okay. I need periodic tables, please. Bailey, can you grab a periodic table under? And you're going to be my periodic table guy. So what's the mass of nitrogen? 14. So 14 divided by 14. 14 plus 14 is 28. Divided by 28, 31. How many percent? Huh? 32. How many percent? 7.5%. Okay. Wait, what's the correct answer? 19 is A. 19 is A. Let's just pick any one here to prove that this is the highest. How about this one because it looks long? Sodium is what?
It is 22.9.
22.9. Nitrogen was 14. Oxygen is 48. Hey, what's the total of this? Plus, plus, plus. 85? 85? Okay, 85 grams. So how many percent is 14 of 85? 14 divided by 85, 60 something. Okay, anyway, 60 something. So A is still the correct answer. That's the highest percentage of nitrogen. Okay, simple math. Number 20. Fun. Concentration question. So, you're given volume, you're given concentration. Perhaps you can calculate for the mole, right? Because you're given concentration and volume. You added it in the volumetric flask, and then your new volume, your new total volume is 500 cm3. What is the concentration of your solution? Okay, so mole here is 2 times 0.005. What's my mole, guys? I don't like zeros. 1 mole of Na2CO3. So the question is, what is the concentration when I mix it with water? Okay, so the mole, as you calculated, is 0.01 mole. And the volume, the new volume, total volume is 500 cm cubed. Okay. Sorry, I just really hate zeros and decimal places. Calculator, what is this? 0.02. Huh?
So it's a circle, then it's wrong.
If it's,
If it's a circle on the paper, then it's wrong.
yeah. Did I mark wrong if it's correct? Okay.
Okay.
So this is mole per dm cube. Correct answer is C. Number 21. You have a compound. The molar mass is 102. It's made up of carbon, hydrogen, and oxygen. What is the molecular formula? Remember, assume percent is grams. I did mention that, right? Or no? Did I mention that? In percent composition, assume percent is grams. If I haven't, now I'm mentioning it. So, 58.8 grams of carbon. So you get the mole. 12 grams of carbon, 1 mole of carbon. Calculator. Thank you. 9.8 grams of hydrogen. 1 gram hydrogen, 1 mole hydrogen, 9.8 mole hydrogen. How about oxygen? 31, 31 grams of oxygen, 16 grams of oxygen, 1 mole of oxygen. 31? 31 divided by 16? 1.9 mole. Okay? So divide all by the smallest mole. So divided by 1.9, 1. Divided by 1.9. Is this 3? Divided by 1.9.
2.5. 5 divided by 2
Wait, wait. What is this? 2.5. Okay. 9.8 divided by 1.9. 5? Okay. Now, remember I also mentioned that the empirical formula or molecular formula should be whole number ratios, right? This is, that's a good ratio, but this is not whole number. So multiply everything by 2. So this becomes 2, 5, this becomes 10. Okay. Suddenly my computer is slowing down. So the correct answer is C5H10O2. Next. Um, CJ, do you have anything in your laptop? Because it suddenly slowed down. Like, are you downloading or uploading? All right, next. So you have this chemical reaction. You have 5 mole of your first reagent. So this is 5 mole. And 6 mole of CO. What is the limiting reactant and how many moles of excess reactant remains? So some calculations here. Number 1. If, okay, I know you know this, but for the sake of everyone, I'll show the full calculation. So if we start with 5 mole of Fe2O3, 1 mole of Fe2O3, choose any of the product. So I'll just choose this. 1 mole of Fe2O3 produces 2 moles of iron. So 5 times 2 is 10. But if I start with 6 mole of carbon monoxide, 3 moles of carbon monoxide is needed to produce 2 moles of your iron. Therefore, this produces 6 times 2, 12 divided by 3, 4 mole of iron. Therefore, which is my limiting reactant? Obviously, 6 mole of CO, because I only form 4 mole of my product. Why are you taking slow? For a while, guys. Okay, I think that's much better. But it's very... Okay. So I know that my CO is my limiting, so eliminate C and D. Question, moles of excess reactant remaining. So if I start with 6 mole of my carbon monoxide, because I know that's my limiting reactant, for every 3 moles of carbon monoxide, I react it with 1 mole of my excess reactant, which is Fe2O3. So, equals. The 6 mole of CO reacts with 2 moles of Fe2O3. Okay, it only needs 2 mole of Fe2O3. But in the problem or in the experiment, you're given 5 moles. But you don't use up everything because according to my calculation here, you only need 2 moles of your excess. So 5 minus 2 is 3 moles remaining. So you still have extra 3 moles. The correct answer is B. Number 23. Which sample contains the largest amount of oxygen atoms? So you start with 2 mole, P2O5. 1 mole is 6.02 times 10 to the 23rd molecule. And in 1 molecule, you have 5 atoms of oxygen. Calculator, please. To those who got this right, can you just give me the number? Times 10 to the power of? Okay. For B, what's your answer, Dorothy? But times up 0, so did you do 0 0.2? 0 0.2 times 6 times 5. It's, so 6.02 times 10, 23? Okay. For B, this is so funny. I think it's like the news, like the main newscaster says, okay, let's rain is in this province and he's reporting live, and then rain goes like this. Yes, thank you. Whatever. I always thought like, can they do something about that because it irritates me. They always do that. Pause. Because the sound. Yeah, but if I was a newscaster, if I hear let's hear from Rain, I'm gonna start talking because it means by the time he finishes the sentence, it's me, right? I don't know. They should, because it's annoying. This is what's happening right now in my laptop. See, there's a 2 second delay. All right. So 1 mole of your oxygen is 6.02 molecules. 1 molecule is 3 atoms. Calculator. 0.3 times 3 times 6.02. To what power is this? B?
Oh, 5.418 times 10 to
5.4 up because wait, but 0.9. Okay, what? 5?
0.418 times 10 to the 23rd power.
Okay, that's less than 6.02, right? So go ahead and calculate for C and D. I'm just telling you that's also smaller than 6.02 times 10 to the 23rd. The correct answer is A. Number 24, almost. Concentration, again, in mole per volume. So what are we given? 0.04 mole. Our volume is 0.2. I don't like zeros. The correct answer is 0.4 mole per dm3. So that's letter D. Number 25. Which volume of gases at standard temperature and pressure have the same mass as 100 cm cube of O2? All right. Let me just solve for 2 because 2 is wrong. 100 cm cube of CH4, you know that 22 point, oops. Let me convert first. 100 cm cube of CH4, 1000 cm cube, 1 dm cube. 22.7 dm cube is 1 mole of any gas. In this case, what is the question? Which volume? Same mass. Okay, 1 mole of your CH4 is 12 plus 1 plus 1 plus 1 plus 1, 16 grams CH4. Okay, calculator, what is this, please? 1000 times 16 divided by 1000 times 22.7. 0.0. Okay, grams. Is it the same mass as this? Let's see. 100 cm cube of oxygen, 1000 cm cube, 1 dm cube, 22.7 dm cube, 1 mole of any gas. In this case, it's oxygen. 1 mole of oxygen is 32 grams of oxygen. Calculator, please.
0.1409.
0.1409. So obviously, that's not the same mass. So 2, Roman numeral 2 is Wrong. So this is wrong. I don't want to calculate. You want me to calculate, or are you okay if I say 1 and 3 is the same? That's fine. But anyway, 2 is wrong. Doesn't match the mass of your solution. 26 was, I said skip, but that's actually easy to get the average mass. Number 27, what is the concentration here? So concentration is mole per volume. We are given, but we're mixing water into your solution already. So your solution has this volume with this concentration. Obviously, using that, I can calculate for the mole. So the concentration is 0.5 mole per dm³ times volume is 0.2 dm³. 0.5 times 0.2 is 0.1 mole. Okay, so using this mole, substitute here in your formula. So mole is 0.1 divided by the total volume, because you added water, is 0.3. The correct answer, am I doing this right?
So you get the concentration
Hold on. Much of water is added to a solution of, so mole, sodium chloride. Um, Concentration 0.5 times 0.2. Why is this wrong? 0.33. Huh. Who got 27 right? So your answer is C. How did you get 0.2? What am I missing here?
and then divide by 0.5.
Because of the
Because
total
that is,
volume.
that is the rule.
Okay. My brain is slowing down. Sorry. All right. So your mole is 0.1. But your total volume is 0.5 because you have 300 cm cube and 200 cm cube there. So 0.5 dm cube mole. 0.2 mole per dm cube. Is this? Did I also add the previous question about concentration? No, it's a different problem. I was looking at 24, number 24. 24 really gives the total volume. For this one, you have to add both the volumes to get total volume of 0.5 dm³. Okay, number 28 and 29, there should be clean paper here. If you have calculations there, tell yourself, why spend time? You don't have to calculate anything here, right? Remember the time when I...
That thing you made
Yes.
us do when we were about to leave
Okay, yes. So if you see gas, 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 Avogadro said, don't worry about anything. Any 1 mole of any gas is 22.4. This is also gas, gas, gas. Raise your hand if you did calculations here. Okay, pretend I have a water gun. Psh, psh. Who else? If you guessed, you did. Psh. Okay, I just shot you with a water gun. No calculation, please. All right. Okay, okay, double check. 2 moles is 5 dm cubed. Therefore, 1 mole is 2.5 dm cubed. 1 mole is 2 dm cubes, which is my limiting reactant. Obviously, 2 dm cubed. That's smaller, right? So 1 mole is 2 dm cubed. How many moles of product do you have? 2. If 1 mole is 2 dm cubed, then 2 mole is 4 dm cubed. No thinking. Number 29. The same thing. If you have 40 cm cube sulfur dioxide, 20 cm cube oxygen, 2 moles is 40 cm cube. Therefore, 1 mole is 20 cm cube. Here, 1 mole is also 20 cm cube. There, neither is limiting here. We need them equally. But you know that 1 mole is 20. So in your product, you have 2 moles of your product. Therefore, 2 moles is 40. Okay, last stoichiometry here of your substance. 0.1 mole of that. I'll just put a smiley. 1 mole of this substance, Avogadro said, is 6.02 times 10 to the 23rd molecules. And in 1 molecule of that given substance, how many atoms do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 atoms. Calculator, please. What's the answer here? Which is letter D, 6.62. All right, good. So rest for 1 minute. Let's go to short answers. Okay. Time is up for resting. Okay, so you're given this chemical reaction, and the only thing you're given is you use 2.478 grams of phosphorus, that's P4, to make pH3. Okay, pH3 is phosphine. Now calculate the amount of white phosphorus used. So if you have 2.478 grams of phosphorus, you know that, to those who got this right, I need assistance to fill out some numbers. 2.478 is, how molar mass please? P4. 100 or 124 grams of P4, 1 mole of P4. Calculator, what's the mole? Or 0.1 and 0.02 mole, rounded. If you didn't round, that's fine. Next, the phosphorus was reacted with sodium hydroxide, so that's the other reactant. Deduce which one is your limiting reagent. Now, if I have 0.02 mole of P4, I wonder how many moles of, moles of phosphine do I produce? So for every 1 mole of P4, I produce 1 mole of pH3. So 0.02 mole of my product. But if I have this of my other reactant, I wonder how many moles of products do I form. So you have 100 cm cube and 5 mole per dm cube of NaOH. Using that given, you can calculate for the mole of sodium hydroxide, which is concentration times volume. Concentration is 5 times 0.1 dm cube is zero point 0.5 mole of NaOH. Looking at the equation, I need to react 3 moles of NaOH to produce 1 mole of my phosphine. So 0.5 divided by 3 is
Oh, I did.
0.17. 1 divided 0.166. Am I doing this right? Or you did a different
I
math?
got a different.
Okay. So obviously that's much more product than when I use 0.02 P4. So my limiting reactant is phosphorus because I only form 0.02 mole of my product. I. Whew, whew. There you go. Okay. Determine the excess amount of my other reagent. So I'm really sure that my P4 is my limiting. So 0.02 P4. 1 mole of my P4 reacts with 3 moles of my other reagent. So I only need 0.06 mole of NaOH. But in fact, how many moles of NaOH do you have? 0. Wait, 0.5. So, therefore, 0.5 minus 0.06 is 0.44 mole of NaOH. I may be doing this fast. I'm recording this so you can watch the explanations again if you want. Okay, so that's the excess that I didn't use, 0.44. Last, determine the volume of phosphine measured at standard temperature and pressure that was produced. So given that this is my limiting, 1 mole of P4 produces 1 mole of pH3. It's a gas, so I know that 1 mole of any gas will produce 22.7 dm cube volume. But the question is in cm cube. So, continue. 1 dm cube is 1000 cm cube. So, calculators. 400, 440 cm cube of pH 3. Did I get that right? Point oh two.
It's 454.
Yeah, my calculator, sorry. 454. Sorry, my calculator. All right. Next question. Why is it slow again?
This is the worst.
Say the equation for the reaction, guys. By the way, if you see ECF, it means error carried forward, meaning it's wrong, but because you got the equation wrong, your calculation was wrong. So I assumed it to be correct because it's just an error carried forward. But in the future, please don't relax and say, oh, it's okay, Miss is gonna just give me error carried forward. It's not all the time. It's the first time, so I'm like, okay, it's fine.
So you're taking off.
For the equation, yes, that's correct.
I thought it was
ECF. I think that's the same in math. You also do ECF. Am I right? Error carried forward.
half the
So you really get it wrong if you get the first wrong. Oh, maybe I should do that too. Okay. All right. You have magnesium plus HCl forms your gas and your salt MgCl2. You have to try to put state symbols. By the way, you didn't. So in the future, please do. Magnesium, is a solid. HCl, is aqueous. It's not solid. H2, that's probably a gas. And the salt, if it's aqueous, then this is aqueous. Okay. Did those who got this right, please just put those changes.
State in the same.
The balancing is Mg2HCl, H2MgCl2. So everything will be ruined if you can't balance it. Remember, balancing gives you the ratio, the mole ratio, so you can do stoic accurately. Determine the limiting reactant. You're given 7.4 grams of magnesium, and you have 15 cm cube volume, 2 concentration. So which one is my limiting? So let's start with magnesium, 7.40 times 10 to the negative 2 grams of magnesium. Molar mass of magnesium, guys. Molar, hello?
Of magnesium, 20,
Hallelujah.
24.3.
24.3 grams magnesium, 1 mole magnesium. Look at the balance equation. 1 mole of magnesium produces 1 mole of hydrogen. Calculator. 0.003 mole of H2. If I start with this HCl, so mole of HCl, first of all, concentration times volume, which is 2 times 0.015. The mole is 0.03 mole of your HCl. You know that 2 mole, this is where balancing is important. 2 mole produces 1 mole of hydrogen. So 0.03 divided by 2 is 0.015 mole of hydrogen. Okay, you make much less hydrogen if you start with magnesium. Therefore, magnesium is your limiting reactant. Next, calculate the theoretical yield of your hydrogen gas. We just calculated it on top. So just bring back your answer here, 0.003 mole of hydrogen gas. Calculate the theoretical yield in cm cube. So you know that 1 mole of hydrogen gas is 22.7 dm cube. And you know that in 1 dm cube, you have 1000 cm cube. So the final answer is 68.1 cm cube of hydrogen gas. Did I get that right? Is it 68? 68. Oh no, I made a big error because I'm alone here. Nobody's talking with me. Okay, good, good, Austin. Look at the question. Under the stated temperature and pressure. So our temperature is 20 degrees Celsius. Our pressure is 1.01 times 10 to the fifth Pascal. So we need to know the volume. We have the mole, temperature, pressure. Maybe you need PV and RT, right? So N, mole, and you didn't do M&Ms here. Uh, no, volume. We just calculated for, we need the volume. So volume is nRT divided by P. Our mole is 0.003 times 8.31 times temperature is 293 divided by 1.01 times 10 to the fifth. Answer is 69. What's the, this is PA? Yeah. This is M cube already because PA is M cube.
Oh, that's not safe.
Okay, so give me the M cube first. Go. 0 point. Sorry, again.
3.669 times 10 to the
Fifth. Fifth M cube. And then just convert 1 M cube is 1000 dm cube. 1 dm cube is 1000 cm cube. Final answer is 36.69, so 36.7 cm cube.
Oh, this.
Yes,
That's the elf. Not the elf.
that's the ECF.
Yeah. So I got it
Okay.
different one. So it's the wrong point 0.000.
Okay, 0.000. How many zeros? 1, 2, 3, 4, 5. 4 after the decimal. 1, 2, 3, 4, 7, 2, 3. M cube. Okay, convert that to cm cube. 1 m cube, 1000 dm cube. 1 dm cube, 1000 cm cube. 1, 2, 3, 4, 5, 6, 7. What? 72.3 cm cube. Austin, you got it wrong, but you're not writing the correct answer. You know what? Don't. So if I ask this question again, then you'll not remember how we did it. 72.3 cm. All right. Almost. See, you can finish the test in 1 hour and 15 minutes. Okay. So you have silver oxide. You heat it so high to decompose them into silver and oxygen. So after heating, you only have 3 to 7 grams of silver remaining. Determine the empirical formula. So 3.760 minus 3.275, so 0.485 grams of silver. What's the molar mass of silver, please?
107.87.
So 108 grams of silver, 1 mole of silver. So that's 0.485 divided by 108 is 4.49 times 10 to the negative 3. How about our oxygen? Wait, sorry, this is oxygen. See, you're not with me anymore. 0.485. The difference is the oxygen. Oxygen. 16 grams oxygen, 1 mole of your oxygen. Should I skip? I think everybody got this right. Yes?
Get to
Yes?
for
It's basically 1:1, right?
Yeah.
AgO. Um, this is from the sample test, am I right? So what could be errors here? Why after heating it's greater than 3275? Obviously there's still oxygen. There are still excess oxygen in your sample. Or maybe your temperature was not high enough to decompose silver oxide into silver and oxygen. So you need to raise your temperature. Only 2 marks there. Or perhaps while you're burning, there are excess or added other gases in the air. There's nitrogen, there's also hydrogen. So that could have mixed with your sample while you're heating it. That's why the mass is higher. Okay, last, almost, yay. Guys, I want to keep you 5 minutes, just 5 minutes, please. All right, 17 grams of C3H7. When you heat it at this temperature and pressure, this is the volume. Calculate the molar mass. I told you already, the hint was mole is M&Ms. So substitute molar mass is MRT over PV. The correct answer is, can you just give me the correct answer? 80? 86 point something. Okay, 86, 86, yes.
why is it centimeters cube is supposed to be in DMQ, not meter?
Your KPA, so DMQ.
Or you could just turn KPA
To PA,
into
yeah,
and then use
MQ. Remember the mnemonic is PAM, Pascal MQ, KPA DMQ. Why are you standing up? I want you here. 5 minutes, guys. Let's just sit down. Okay. Molecular formula of your compound. You're given C3H7. So 12 plus 12 plus 12 plus 7 is 43. So your sample is only 43, but when you calculated there was 86. So 86 divided by 43 is 2. The actual molecular formula is C6H14. Okay. Next, HCl, that's your monoprotic acid. You're titrated with sodium hydroxide. You're given concentration and volume, so meaning you can calculate for the mole. Concentration is 0.1. Guys, can you just stare at the screen, please? 0.025 dm cubed. What's the mole? Everybody got this right? What's the mole?
0.0025.
Oh, that was in the practice.
Mole of NaOH. Then the last question is calculate the molar mass of the acid. You know that 1 mole of your base reacts with 1 mole of your acid. So the mole of the base is the mole of the acid. And you're given the mass. So M&Ms. Calculate the molar mass. I think 2 people got this right. Got this wrong. So N equals M over M, which means molar mass is mass divided by mole. The mass is 0.510 grams. The mole is 0.0025 mole. Okay. What's the molar mass? 204 grams per mole of your unknown acid.
Also, it's saying that it's HCl. It's just the if. So
Yeah,
it's
that's an example of a monoprotic acid. HCl. All right. Please make sure to fill out the reflection form on Google Classroom, preferably today, because I'm finishing your comments for the grades. I want to see how you reflect on topic one, so I can have a better comment in your report card, please.
Maybe Friday.
Come back later.
Oh, okay.
Put it here. I'll pick it up later. Do I need reflection? Do I need reflection for the test?
Yes.
Asija, you filled it out already. Thank you. The rest of you, you
Actually,
have
I'll
until
just-
today, please.
I'll just come back later.
Okay.
Come back.
When do I need the reflection? Tonight. Today.